My name is Armin Hadzic. I will be presenting our work titled Handling Image and Label Resolution Mismatch in Remote Sensing. This is a collaboration with Scott Workman and Usman Rafique. Overhead imagery is diverse and comes in many formats. This diversity leads to unique challenges when applying semantic segmentation algorithms. For example, how to handle resolution differences between input imagery and target labels, a problem we refer to as resolution mismatch. In this work, we explore how to generate fine-grained predictions when only low-resolution labels are available for direct supervision. Our key insight is that exemplar high-resolution labels are often available, and that a method should be able to take advantage of this auxiliary data during model training without the corresponding imagery to aid in producing fine-grained output. As high-resolution imagery has become more available, the cost of collecting pixel-level annotations that match the image quality has become increasingly apparent. In practice, it is much easier to obtain coarse, low-resolution labels. Existing strategies for learning from low-resolution labels either 1. Ignore the resolution mismatch problem entirely by naively upsampling the target label, 2. Consider only partial or image-level labels, or 3. Require statistical information relating the distribution of high-resolution labels to low-resolution labels during the learning process. Instead, we explore how to generate fine-grained predictions from low-resolution supervision without upsampling by taking advantage of an exemplar set of high-resolution labels that has no spatial correspondence to the input imagery. Extensive experiments showed that our approach significantly reduces the performance gap compared to a high-resolution baseline without the need of high-resolution supervision. We present a framework for semantic segmentation in the event of resolution mismatch. Our method has several key components. First, it incorporates the concept of region aggregation to allow the network to output native resolution predictions without upsampling the low-resolution target labels. Second, it uses adversarial learning combined with an exemplar set of high-resolution labels to encourage predictions to be fine-grained. Third, it leverages self-supervised pretraining on a large set of unlabeled imagery to increase model generalization. The result is a method which bridges the performance gap between naively upsampling available low-resolution labels and assuming the existence of expensive high-resolution labels. To support our experiments, we introduced the low-to-high dataset, an extension of the Chesapeake dataset, to address the resolution mismatch problem as well as supporting self-supervised learning. We show example labels from our merge label taxonomy above, along with example images from the auxiliary dataset on the left. Using the low-to-high dataset, we studied the impact of label resolution on predictive performance, evaluating all methods against the high-resolution labels. In other words, the goal is to examine how well each method performs relative to the high-resolution baseline, which represents optimal performance. These results highlight the performance costs associated with naively upsampling the low-resolution ground truth. Next, we conducted an ablation study to explore the performance impact of individual components. The inclusion of appearance-based adversarial training proved crucial for obtaining the best performance. In addition, we used auxiliary imagery from our dataset to study the impact of self-supervised learning on model generalization using reconstruction as a pretext task. Pretraining significantly improves performance when transferring a model to a novel location. Finally, we evaluated how the performance of our proposed approach changes with respect to the quantity of exemplar labels used during model training. Very few exemplar high-resolution labels are required to surpass the performance of the low-resolution baseline. In conclusion, we propose an end-to-end architecture for semantic segmentation that is supervised using low-resolution annotations, but is capable of generating fine-grained predictions. Experiments on a novel dataset demonstrate the potential of our approach to have real-world applicability in the remote sensing domain.